So the first big one I want to talk about, and again, this is a non-exhaustive list of everything, but the first one I want to talk about is how you decide to go about encoding a qubit into a photon, right? Because we've talked about how the way you transmit quantum information is with light, right? But you need to do it in a quantum way, i.e. somehow encode a qubit state, a quantum state, into a state of light. And there are many different ways of being able to do this. We're only going to talk about a couple here, as these are kind of the most presently used currently, but as the industry evolves, we'll get more and different kinds of encodings, higher photon number encodings, etc. Here, we're dealing with single photon encodings, i.e. your qubit is encoded into the state of a single photon particle of light. The first that we'll talk about, and this is kind of the easiest to make, but it's also the most susceptible to loss on fiber, is called a single rail qubit, also called an absence-presence qubit. This is because, in this case, the 0 and 1 of a qubit are encoded as the absence or presence of a photon itself. So if you have a 0, you have no photon. If you have a 1, you have a photon. But again, you can also have superpositions of these. This is a quantum system. And so you can literally have a superposition of a photon existing and non-existing. So that's pretty cool. But for usefulness purposes, it's not so good, because if your photon gets lost along the way, how do you know if you received a 0 or no photon or no qubit? So for that reason, we want to be able to know when we actually received our qubit or not, and that's what dual rail qubits are good for. This always uses a single photon, but it is distributed between two independent optical modes, or again, a superposition thereof, because we're dealing with quantum. So different kinds of dual rail qubits include polarization qubits. This is where a qubit is encoded into the polarization of a photon, right? If it's horizontally polarized, it's a 0. If it's vertically polarized, it's a 1, or in between. You can also use any other degree of freedom, like where that pulse or that photon actually is, right? So say that you have two pulses coming down, or a superposition of a photon being here and being here. That's called a time-bend qubit, because if your pulse arrives early, then it's a 0. If it arrives later, it's a 1. And you can also do this with frequency or combinations of these things, right? And again, this is only the beginning of the ways that we can begin to encode qubits into light. And hopefully this gives you a sense of the ways that you can do this. And each of these different options has different corresponding requirements for hardware and how you actually do it. And so understanding what hardware you want to use is really important for understanding what type of encoding you want to use. A very large requirement for any of this is clock synchronization between your nodes. I've mentioned this before, that you require the nodes to be highly synchronized, and this is because there are a variety of reasons, but in general, because these quantum systems are very precise with how they interact with the environment and themselves, you have to be very, very precise. For example, there are certain kinds of quantum memories that can store a qubit coming in as a photon very well, but it has to know when to expect that photon. And so if that was sent by some other node and you're receiving this, you need to know exactly when that guy sent that photon to be able to know exactly when to expect it. And so having that high level of synchronization is important for this task. Another example is in entanglement swapping. There are various ways of doing entanglement swapping, but it often requires you to have high synchronization, often down to the picosecond level, between when your photons will arrive at this repeater. And so having this high time precision is a challenge, but it's doable. But you have to understand how you're going to be going about that in your context.